In CATIA, geometry can be controlled using parameters and formulas. This is where the term parametric modeling is derived from, where adjusting the values of the parameters will result in a change in the geometry. In this step, we will add some common wing planform parameters that we can use to control the shape of our wing. In the Tools toolbar, click the Formula command. Select the type of parameter required in the drop-down menu, for example, the wingspan is a length. Click the plus icon to create a new parameter. Rename the parameter by selecting the parameter in the table and then clicking the name text. Adjust the local name in the pop-up. Adjust the value of the parameter by double-clicking the value column. Create a parameter for each row in the table shown on the left, using the correct type and value. Click OK when you have finished creating all the parameters. As you can see, the parameters created are now shown in the model tree. By double-clicking a parameter, you can change the value of it. If you cannot see the parameters in the tree, check the Adjust Preferences video on the dashboard. In this step we will add a geometrical set to contain a sketch of the wing planform. In the Essentials toolbar, click the Geometrical Set command. In the dialog box, name the geometrical set as wing planform, then click OK to create it. Make sure the new geometrical set is the in-work object. This is shown by it being underlined. Create a position sketch on the XY plane. Use the Profile tool to create the wing planform shown in the image on the left. Now create a construction line as the quarter chord of the wing. Dimension the sketch as shown. Do not worry about adding the correct value as we will use formulas to calculate the value of the dimensions instead. To add a formula, right-click a dimension. In the Item Name Object menu, choose Edit Formula. In the dialog box, the text field shows the current formula for the object. To insert a parameter into the formula, either find it in the list of parameters and double-click it, or double-click the parameter in the model tree. Ensure that the correct formula is shown in the text field and then click OK. As you can see, the constraint now has a FX symbol to denote that it is controlled by a formula. Add formulas to the rest of the dimensions as shown in the image. When creating formulas, the units are very important. For example, if you add two lengths together, CATIA will always convert to SI units, so if in the case of a length it will assume it is in meters. Exit the sketch when you are finished. A powerful feature in CATIA is to use macros to automate repetitive tasks. One of these tasks that concern the design of wings is creating airfoils, and since NACA profiles are quite common, we will use a macro that was written to quickly create a NACA 4 airfoil. In the Tools toolbar, click the arrow next to the Material browser to expand the toolbar. click the Macros command. In the Macros dialog box, click on the Macro Libraries button. In the drop-down menu, choose PLM Directories and then click on Add Existing Library. Search for the macro library with the name given and then select the item in the search results. Click Close in the Macro Libraries dialog. Select the NACA 4 Airfoil file and then click on Run. In the first pop-up, enter in 2412 as the NACA profile. In the second pop-up, select Yes to keep the trailing edge open. In the third pop-up, enter root Airfoil as the name for the profile. Click OK in the Script Complete pop-up. As you can see, a set of parameters, formulas and geometry are automatically created. Expand the set of parameters and add a formula to the chord parameter, C, which equals the root chord parameter. The reasoning behind using an open profile is because it is typically more stable when making surfaces, as it has a clear starting and ending point. Whereas a closed profile does not, and the direction of the curve is therefore not always consistent. In this step we will create a line on the chord of the airfoil, which we will use as the axis of rotation in the next step. In the wireframe toolbar, click the Line command. Use the drop-down menu to change the type to point direction. Right-click the point field. Under Insert Wireframe, choose Create Point. In the Point dialog, use the drop-down to change the type to On Curve. In the Curve field, choose the chord line of the airfoil in the model tree. Change the distance to reference option to ratio of curve length, and set the value to 1, so that the point is created at the end of the chord. If not, change the direction by clicking the arrow. Click OK to create the point. Now in the Line dialog box, in the Direction field, right-click and select the Y-axis. Set the offset to 250 mm and add the Symmetric option. Click OK to create the line. In this step we will use the line from the previous step to rotate the airfoil using the incidence angle. In the Transform toolbar, click the Rotate command found underneath the Translate command. Make sure the axis angle type is selected. Select the airfoil profile curve in the model tree as the element to rotate. Select the line from the previous step as the axis. In the Angle field, right-click and select Edit Formula. Insert the incidence angle parameter into the formula. Click OK to confirm the formula. Click OK to create the rotated curve. Now we can hide the original airfoil profile to keep the geometry clean. In this step we will use the macro again to make an airfoil for the tip of the wing. We will start by hiding the root airfoil geometrical set, to make the next few steps a bit easier. Right-click the geometrical set and choose the Hide Show option. In the Tools toolbar, click the Macros command. If the toolbar is not showing the Macros command, click the arrow next to the Material browser to expand it. The macro library should still be loaded, if not, refer back to the previous macro step in order to find how to load the macros. Select the NACA 4 airfoil file again and then click on Run. In the first pop-up, we will keep the 0012 as the NACA profile. In the second pop-up, select Yes to keep the trailing edge open. In the third pop-up, enter Tip Airfoil as the name for the profile. Click OK in the Script Complete pop-up. Again, we have a new set of parameters, formulas and geometry. Add a formula to the chord parameter which equals the tip chord length this time. Just like the previous steps, we will repeat the rotation of the airfoil, but we will add the twist angle to the rotation. In the wireframe toolbar, click the Line command. Use the drop-down menu and ensure that the type is point direction. Right-click the point field. Under Insert Wireframe, choose Create Point. In the Point dialog, use the drop-down menu and ensure that the type is on curve. In the Curve field, choose the chord line of the tip airfoil in the model tree. Check that the distance to reference option is set to ratio of curve length and set the value to 1. Click OK to create the point. Now in the Line dialog box, in the Direction field, right-click and select the Y-axis. Set the offset to 250 mm and add the Symmetric option. Click OK to create the line. Now we will rotate the airfoil. In the Transform toolbar, click the Rotate. Make sure the axis angle type is selected. Select the tip airfoil profile curve in the model tree as the element to rotate. Select the line that we just created as the axis. In the Angle field, right-click and select Edit Formula. Insert the incidence angle plus the twist angle parameters into the formula, as the twist angle is defined as the rotation between the root airfoil and the tip airfoil. Click OK to confirm the formula. Click OK to create the rotated curve. Now we can hide the original airfoil profile to keep the geometry clean. We now need to move the airfoil to the end of our wing to be able to create the wing surface. So in this step we will translate it. In the Transform toolbar, click the Translate command, which will be under the Rotate command that we used previously. In the Translate dialog box, select the Point-to-Point option as the type to be used. Select the rotated tip airfoil profile from the previous step in the model tree as the element to translate. Select the tip airfoil leading edge point in the model tree as the start point. Select the tip leading edge point of the Planform sketch in the geometry for the end point. Click OK to create the translated curve. As you can see, the curve is now translated by the distance between the 2 points. As with the previous steps, we can hide the rotated tip airfoil and the rotation axis. In this step we will create 3 lines that will help to guide the surface of our wing. Start by showing the root airfoil geometrical set again and then hide all the other geometry elements except for the 2 correctly positioned airfoils to help clear up the geometry window. In the Essentials toolbar, click the Geometrical Set command to create a new geometrical set and name it Wing Surface. In the Wireframe toolbar, click the Line command. Use the drop-down menu to change the type to point to create a line between 2 points. Select the leading edge point on the rotated root airfoil as point 1. Although it may seem that there is no actual point, the way that the curve is created with the upper and lower curves being joined together allows us to still use the vertex that is in that position. Select the leading edge point on the translated tip airfoil as point 2. Ensure that both offsets are set to 0 mm. Click OK to create the line. Repeat the procedure and create 2 trailing edge lines with the points at the end of the profile curves. Rename the lines as leading edge, trailing edge top and trailing edge bottom, respectively, by right-clicking the line and selecting Properties. In the Feature Properties tab, change the feature name to the corresponding name of the line. In this step we will create the surface of the wing using a multi-section surface. As the name suggests, it is a surface made from several sections located along a span. In this case we will be using the airfoils as the sections. In the Surface toolbar, click the Multi-Section Surface command. Select the rotated root airfoil as the first section, and the translated tip airfoil as the second section. Ensure that the arrows of each section are pointing in the same direction. If we click Preview now and look at the leading edge, we will see that the surface is not very good. The light gray lines show that there are several faces being created at the leading edge, with none of the edges connecting the leading edge points together. In order to create a better surface, we will use guides to help align the different points of the sections. Click the Guides field to activate it. Now select the 3 lines we created in the previous step as the guides. Click Preview again to see that the extra face is now removed. Click OK to create the multi-section surface. As you can see now, the surface is now made of only 2 faces, with the leading edge separating them. This step will be used to show how creating the wing with all the parameters allows us to quickly change the shape of the wing and demonstrate the power of parametric modeling, because instead of remaking the wing to get a different shape, we can adjust the parameters and it will automatically update. Double-click the root chord parameter and change the value to 2000 mm. Then click OK. We see that the root airfoil has increased in size and the shape of the wing has adjusted to the new profile. If we wanted to change the camber of the tip airfoil, we just need to change the NACA 4 parameter for the tip airfoil. In this case we will try an asymmetric profile similar to the root airfoil and see the result. Try adjusting the different parameters to see how the wing updates and is affected. Once you have tried different combinations of values, adjust the parameters to the values shown in the image on the left.